Well, I'm Daniel. I'm software engineer at Elastic, and I'm mainly concerned with performance-related topics at Elastic, especially with regards to Elasticsearch. Okay. And there is a little tool I've built over the last few months. It's called Rally, for a reason, actually. And today I want to talk about Rally and benchmarking in general. So this is not so much about Elasticsearch, but more about performance in the context of Elasticsearch. Who of you has ever run a benchmark or a load test or something like that? Which tools did you use? JMeter, probably? Anything else? Gatling, okay. Grinder maybe also? Nobody? Okay. Grinder exists also. Did you ever run a benchmark or a load test against Elasticsearch? Pardon me?
Against Lucene.
Oh, okay, against Lucene. This won't apply to Lucene. Okay. So we did this also previously. We also had a bunch of scripts running internally for benchmarks, and Rally is basically the evolution of that. So, well, Elasticsearch, as you all may know, is just a search engine, right? It's just a search engine. And that's correct, it's a search engine. So you can search things and eventually you will also find something. And Elasticsearch is mostly known in the context of, or is known in the context of full text search. But search is not only search, you can do also structured search, you can do geo search. So there's a lot of different things you can search. Two examples are all the search on GitHub is powered by Elasticsearch, for example, and also the search on Wikipedia is powered by Elasticsearch. Those are totally different websites, right? Then we also have the logging or metrics use case. You've probably expected some kind of web server here, but instead I've put another thing, namely Curiosity, the Mars mission of NASA here. They also put all the metrics of the Mars rover into Elasticsearch. And then for sure you also have security analytics. So this is a different approach. For example, the Mozilla defense platform is built based on Elasticsearch for security incidents inside Mozilla. So the question is, it's not just a search engine. Those are totally different use cases, and we have the problem. We build a product, and we want to ensure that the performance is good in all those cases, whatever performance means and whatever good means. And our problem is we don't just have a single defined use case, and for that we can test. We have lots of use cases out there, and for that we need to run tests. And this is what we do. We measure, and we measure a little bit more. For example, during development, this is a concrete ticket we had recently. This was the decision whether we should enable HTTP compression by default or not. And we ran quite some benchmarks on that and decided to enable it by default, and also settled on a default compression level, which was quite a good compromise between not losing too much latency but still getting better usage of the available bandwidth. Second thing is, you might notice if you're a Java developer, this is Oracle Mission Control. We also profile Elasticsearch. We have nightly benchmarks running, and we publish them also for different use cases. I'll get to that in a minute. We also have sizing benchmarks, which means how does Elasticsearch scale. I've, by intention, removed the axis. Those are stripped because the actual numbers are not of interest, and it's actually an internal picture. We also do performance evaluation at customer sites. For example, this is latency. Those are latency spikes over time. We've identified at a customer and analyzed what's going on. So we measure a lot, and I want to show you now how we measure. And this is where this little thing comes into play, namely Rally. Rally is available as open source, for benchmarking Elasticsearch. And the key goals were that it's easy to set up and use, and that it eliminates common benchmarking flaws, which I'll talk about later. And it allows you also not to say, okay, here is some number that I determined, but instead it also allows you to dig deeper. Why is this number reported? What's happening? Why is it so slow? And then you can dig deeper with so-called telemetry devices and analyze what's going on. So here is a 10,000 feet view of Rally. First of all, we have this Rally component, and what it does is, as a first step in a benchmark, it provisions the cluster that it benchmarks. Then it attaches these telemetry devices, which measure, for example, throughput, latency, CPU utilization, memory, whatever. And these report system metrics to Rally. Then we have something called tracks. In this race analogy, we had to come up with some race-related names. Tracks are actually the benchmark descriptions. And those live in a GitHub repository, and we see in a minute why. So Rally reads those tracks, or a specific track that you want to run. For example, you want to run a logging benchmark. Then we have a logging track, which describes where the data are, what indexes you want to fill, what queries to run on that. That's the track description. And Rally reads those and says, and then applies loads according to this track specification. So it hits the cluster. And finally, it stores all those metrics in a metric store. We have basically two options. You can have it in memory, which is easier to set up. And you can also have a dedicated Elasticsearch cluster where all those metrics are pushed. We use this option for our nightly builds, as we want obviously have persistence across runs. So we have a time series across multiple runs. So, and now it's time for a little demo. Hopefully not that sweaty. Whoops, you're not supposed to see that. Oh yeah, well, whatever. We skipped the installation part, but what I want to show you is this one. I'll explain in a minute. I hope it doesn't run. Yeah, right. Okay. So this is how you invoke Rally. We have something called pipeline concept, which basically just tells Rally what steps to execute. For example, we as Elasticsearch developers want to run benchmarks against some kind of change we have on the branch, right? So we want to build Elasticsearch from sources. That's why we have a pipeline called from sources. And you maybe don't want to set up all the development environment and just want to know, well, what's the performance of Elasticsearch 1.7.5 against the latest alpha build of 5.0. So you can say from distribution, and then you have to specify a distribution version. And to be honest, Rally assumes a default track that's called geonames. I'll spell it out here just for clarity. It means I want to run it against some kind of geonames data set. We'll look into that in a minute. It's just country data that get indexed into Elasticsearch. And if I start this now, you see here it detects, okay, we don't have Elasticsearch locally here in this version. It downloads it from the official Elastico site. And now it starts the benchmark. Actually, obviously we won't get meaningful numbers because it's run on my notebook. But you can see here it starts now indexing the documents. It reports what's going on at the moment. When indexing is done, it will start searching. This is currently a limitation of its heritage. We eventually will allow much more flexible benchmarks. For example, you can say, I don't know, after 2 minutes or after a certain amount of documents is indexed, I want to start searching with this and that throughput and this and that many clients. So I'll leave that running in the background now, or I'll cancel it. I do something different. I have another pseudo benchmark. It's called Tiny. It's just for development and integration test. It runs much faster, obviously. That's why it's called Tiny. Never run it. You see much faster. And then you can see a command line summary of the results. And if you have an Elasticsearch metric store, you can do much more with that, as we see in a minute. Questions so far? Would be.
This is Python.
Pardon me?
This is Python. Yeah?
This is Python, right? How did you notice?
This is forehead.
Pardon me?
No.
Here. Okay, yeah. It says in the header, right? Yeah. That's also due to its heritage, because the original scripts were written in Python. So, as I picked this up, I didn't even know Python. Okay, fine.
That's the point of Python.
Pardon me?
That's the point of Python.
Okay, I see. So you see a lot of statistics, and actually it's basically indexing throughput and lots of percentile values for each query that has been run, and some system metrics. But this is actually just, well, for your overview. The main idea is that you look at, I first show the metrics records. For each measurement we take, we store a structured sample including a lot of metadata. For example, which concrete source revision did we benchmark, on which host, which kernel, how many CPUs, and all this stuff. So you can make sense of this later on. And for example, I've prepared a benchmark of Elasticsearch 175 against the latest alpha build of 5.0 and compared the indexing throughput in Kibana, which looks like this. The blue one is obviously the new 5.0 version, and the green one is 175. In a specific benchmark on my machine, just for demonstration. So it's probably not that authoritative. But what you can see here is we gather indexing throughput not only just once through the single for one benchmarking run, but over time. So you can see how it changes over time. This is just one benchmarking run, not a whole lot of them. And you can compare them. That's the main idea. You can start to analyze. So maybe let's suppose indexing throughput would be much worse, like around 10,000 documents here. Then you can start to attach telemetry devices. Just a moment. We've currently just 3 of them exposed to users. We use them also internally, but we don't allow you to activate or deactivate them because they're always active. For example, we don't allow to deactivate CPU sampling. So the most interesting for me is most of the time the Java flight recorder. I don't know, did anybody of you use ever Java flight recorder or mission control? One, okay. At least one. It's a great tool actually. It allows you to analyze a lot of stuff. But the thing is, you can just say here telemetry Java flight recorder, and it will run a flight recording, which you then can open in mission control, which I've already prepared. This is a great tool. It comes with Oracle JDK, and it allows you to gather a lot of insights into your Java application. The only caveat is you're not allowed to run Java flight recorder in production unless you have a Java SE advanced license, which costs like big bucks. I don't know how many, but a lot. So I would urge you to look at this. It's a really great profile. So on with the demo. I think I've showed the most interesting things. Right, the tracks. I've spoken before about the tracks, which describe what to do in a benchmark. And what you can see here is that we have branches, different branches for different Elasticsearch versions, because mappings change over time, or configuration in Elasticsearch changes over time, and that's how we manage in Rally that you can benchmark from 1.7 up to the latest master version. Although the mapping changes. And it's basically a JSON format. I won't show it in detail. I will just show you here is basically a description of it. It's rather long, but it's descriptive and not just somewhere in code, and you can somehow easily change it. That's the main idea. Questions? Otherwise I would go. Okay, I go on. I'll speak a little bit now about some topics I've encountered while developing Rally, which usually happen when you do a benchmark. I committed part of those sins myself before, and I think everybody experiences those sins when you start to benchmark. Okay. The first one is actually before you even run a benchmark. You don't pay attention to the system setup. You just say, yeah, I have my developer notebook or whatever, and I start to run a benchmark there. And not a good idea, because you want a quiet machine, a machine that's not experiencing a lot of background noise from other services running on the machine. For example, I don't know, Spotify running on your developer machine. Not a good idea if you want to benchmark millisecond latencies. Of course, you have to pay attention to whether you use SSDs or normal hard drives, which SSDs. You should use server class CPUs, because Elasticsearch runs on a server class CPU in production normally. Why do you benchmark on a notebook? Do you want to run on a single socket, multi-socket machine? These make differences. And obviously you need enough memory headroom for the file system cache and all this stuff. So, but the list goes on. Do you benchmark on Linux, on Windows? Did you disable swap? Did you check your network configuration? Do you have any bottlenecks there? Which file system do you use? Which I/O scheduler do you use? Which CPU governor do you use? For example, by default, at least in most distributions, I think the PowerSafe CPU governor is run, which tries to drive the CPU at the lowest possible frequency in a given range. So if you don't have enough load and you have, for example, you do a lot of I/O, the CPU is probably not maxed out. This means the CPU PowerSafe governor will scale down the CPU frequency during your benchmark, and that's probably not what you want to do.
Right, but the problem is your indexing in search is I/O heavy.
Yeah.
With all of this, that's all what it's about. And it's actually getting your backplane down and getting the data through. And that also depends upon the physical, how many CPUs you have because of also the architecture of the CPUs and how you can get data in and out of the CPUs. That actually defines what you're going to get in terms of performance, time, latency, etc.
Yeah, but for latency, you want to ensure that you run on a constant level for reproducible latency. Maybe it's not that interesting in production, but if you want to measure, you don't want to introduce measurement artifacts due to.
Also run this on a physical.
Yeah, right. Correct.
It's probably the next thing.
Yeah, the physical was the first thing. Bare metal.
Okay.
Don't run it. Yeah.
No, you want to run it on it. You want to run it on a physical. You don't want to put it on a virtual machine.
Yeah, right. Bare metal. I call this bare metal.
Okay, that looks like the SIN.
Oh, this is the not SIN.
Okay.
SIN would be in the cloud, you know. Okay. Yeah, and also the JVM version, but because you know JVM performance doesn't stay constant, it improves usually over time. So it's also important, and that's also why we store the JVM version in each metric sample. Yeah, I could go on now, but I go to the next thing. So the next thing is, well, I don't know about you, but before my first coffee, I'm not awake. Probably you aren't either, and also Elasticsearch isn't either. Each system needs time to warm up, to get up to speed. For example, for every Java-based application, the JIT compiler needs to run in order to bring it into a steady and performance state. So you don't want to benchmark right from second zero. Then the application has to create some long living data structures like, I don't know, caches. The application has to boot up. Then you have the file system cache for the scene segments also has to warm up. It's not there from second zero. And funnily enough, also the benchmark driver needs warm up. It also doesn't reach stable state from second zero, which we'll see in a second. Here's a diagram showing the number of C2 compilation events per second. C2 is the server compiler, basically, the one that gives you the real performance. And what you can see here is, right after the start of the benchmark, we have almost 800 compile events per second. And if you start to benchmark in this phase in the first 3 minutes, you just get bogus results, right? You probably wonder about the second spike around 10 minutes. This is because in the first 10 minutes we are indexing, and after that we are searching. So the JIT compiler kicks in once more because we are exercising a lot of other code paths now. But the gist of this is you have to wait a little bit. Don't take the first samples. Verify that you wait for long enough, that the system is stable. Yeah?
One of the problems, however, waiting up is if you're running the same data through, you may actually get performances which are actually reading from the virtual memory cache, which is loading the file up from, and things look quicker than they really actually are because the file data you're already reading is already coming out of the operating system cache. So you actually have to have a wide distributed amount of data, because if you're just saying, let me just take the same data, slap it through, same data, slap it through, same data, slap it through, this is already sitting there. It's not even actually touching it.
Yeah, sure.
It's sitting up there in the cache is just going, oh, great, and now it's real fast.
No, this is not a good idea. That's, yeah, we have benchmarks of different sizes. I think the GeoNames one is like 8 million records or so, and the largest one is a logging benchmark with, I think it's, I don't know how many records, but it's like 90 gigabytes or so.
Randomizing the various bits and the various combinations that you're pulling out.
No, but these are real data. What we don't do is we never benchmark with synthetic data. We took a real effort to get open and large real data sets. But randomizing is something that's planned for a future release for Rally. So we always exercise the same queries. That's correct. But that's on the roadmap to change that to allow you to randomize, first of all, the order in which queries are run. And second of all, also parameters. You can search in the first few iterations for A and in the next then for C, and so you don't have those caching effects. Okay. As I mentioned, also the benchmark driver needs warm-up. This is the behavior of the benchmark driver against the stub. And you can see here it shows on the y-axis the indexing throughput, and then the x-axis is kind of the time. It's not exactly the time, but it's just sample points. But what you can see here is it doesn't start right from the beginning to with a stable applying load in a stable fashion, but it actually also needs time. So you also need to consider that. Third sin, you don't think about bottlenecks. You just have some kind of number, but you don't know whether you really benchmark what you think you're benchmarking. For example, a bottleneck could be in your benchmark driver, which we'll see in a second, or in your system setup. For example, you have a very noisy background service which is always interrupting and stealing your CPU. That's probably a problem for latency. Or for example, you have a noisy network, or you use like a 10 megabit network, then obviously you can't reach really good performance. So I did a driver stress test, and the results didn't look really promising, because actually we also see again the indexing throughput on the y-axis and the time on the x-axis, and 4 data series here. But the problem is the red one with the highest throughput is with 1 thread, and it goes downhill from there. And the lowest curve exhibits a really weird pattern. It's with 8 threads, and it's contention in multiple places. This was contention when reading a file, and it was also contention during sending. That's why it got slower with more threads. So you wouldn't really expect this if you don't look at this. You would just say, yeah, okay, that's my indexing performance with 8 threads is this. But it's actually pretty bad. Fourth sin, the benchmarking script is divine. You know it produces accurate numbers, so it must be true. And you're not really paying attention to how metrics are gathered. For example, if you look at system current time millis versus system nanotime, system current time millis is obviously not that precise, not as precise or accurate or whatever as system nanotime, but it also has another problem. It's non-monotonic. This means when the daylight saving time changes, it changes. And it also has all sorts of other problems. So when benchmarking, do yourself a favor and use at least system nanotime. If you attach profilers to your system that you're benchmarking, you should also check what's actually the overhead of the profiler, because it will have some kind of measurement overhead. So you should do more runs than without the profiler and with the profiler, and compare those two to see the overhead. Or another funny thing is your system is really fast, but the problem is it doesn't return proper responses, but instead 404s. So, well, it doesn't help you either. And another funny thing is you shouldn't have blind trust in tools, but check tools against each other, which are supposed to measure the same thing, and then try to look at the differences. For example, I did this with GC statistics. I did different runs and compared the numbers of the total young generation time and the total old generation time that the tools reported. And I looked at what Rally reported. Rally uses basically what Elasticsearch gives via the HTTP API, which is in turn uses a JMX bean. Yeah, right. Then I also grabbed the GZ log and I looked at flight recorder. And Rally and the GZ log kind of reported the same numbers. That's okay. But flight recorder was way off, especially for the old generation time. And I wondered, how can this be that it's like 8 times more? And I had a theory, and I approached the mission control guys then, which I ran into by coincidence. And they confirmed the theory. The thing is, in the GC log, Elasticsearch uses the CMS garbage collector. Is everybody familiar with CMS? Okay, nobody's familiar with CMS. Okay, CMS stands for concurrent mark sweep garbage collector, which means it has some phases where it stops the application and some phases where it runs concurrently with the application. So the garbage collector may run for 100 seconds, but it stops the application just for 5, just as an example. Okay. And the thing is, the GC logs and Rally just report the times where the application was stopped. But flight recorder includes these concurrent times too. So if you just look at flight recorder, you might think, yeah, okay, I stopped for 156 seconds. But this is not true. Your garbage collector runs for 156 seconds, but the application is just stopped for 23 seconds. And if you dig deeper, you'll find a lot of things that are similar to that. System, you just run the benchmark once and you're done, right? Probably not. You should Elasticsearch, or in every macro benchmark, you will have some kind of run-to-run variance. Sometimes it's a little bit faster, sometimes it's a little bit slower. Maybe the operating system schedules things a little bit differently, I don't know, the hardware is a little bit nicer to you when you have a running classic hard disk, whatever. You will have run-to-run variance, and what you should do is you should do multiple trial runs for each, for the baseline and for your comparison, and then run a statistical so-called t-test to determine whether your samples are significantly different. And just for completeness, you are just allowed to run the t-test, as far as I know, if the variance is follows a standard distribution, a normal distribution. If it's another distribution, the t-test is invalid, as far as I know. And this is what I did here, for example. Again, indexing throughput. I ran the same benchmark with the same binary of Elasticsearch, with everything the same, a couple of times. I think it was like between 50 and 100 times or so, and did a histogram of the reported indexing throughput. Yeah, now imagine that in one run you had 32,000 as indexing throughput, and in the next run you had 33,000, and you said, yeah, this is a performance improvement. Maybe it's not. Maybe it's just run-to-run variance, and that's why it's important to run multiple trial runs. And the number of trial runs depends on the confidence that you want to gain. The more, the better, obviously. But one is definitely not enough. A special topic in statistics is also latency measurement. There is a whole talk about that. It's linked in the slides afterwards. A lot of people report mean latency. And the funny thing is, this just means that half your customers get a worse response than that. But you don't know how much worse. So you should typically report percentiles. And as we're at percentiles, it doesn't make sense to calculate the 99.99 percentile from 10 samples. You need at least 10,000 samples to calculate that. And when you do multiple trial runs, you also shouldn't average percentiles, because percentiles are always relative to the data set you're using now. For example, maybe the data are in this range in the first trial run, and in this range in the second trial run. It doesn't make sense to average something like that. But the good news is we capture all the raw samples, so with Rally you have at least a chance to calculate the percentile over multiple trial runs then. And latency distribution is not normal distributed, it's multimodal. Think just of garbage collection events. Garbage collection events don't fit. You typically have a lot of responses on the lower end, like say 1 millisecond or so, and then from time to time a garbage collection kicks in and you have a response time of 200 milliseconds. How does this fit into the normal distribution? Not at all. Okay. Sin number 6. We are again kind of in the metrics area, in the latency area. Think of this. First, a user issues a request. Then, at some point in time, you start request processing, and as the first step, the response is returned. And now a lot of people forget that there are little queues in between, and they matter. The first thing is, you usually measure, when you think you measure latency, you're actually measuring service time. You're denying this queuing effect here, and I'm showing why. So you're just reporting on step 2 and 3. Because usually benchmark tools look like this. You run in a loop, you take the start time, you issue the request, you take the end time, and the difference is your latency. No, it's not, it's the service time. If you account for all 3 components, then this is, some call this latency, some call this response time, but this includes the wait time, definitely. So this could look something like this. You have 2 separate threads. One thread is generating the requests regardless whether the request can be issued or not. You take the start time. This is the time the user hit on the browser, on the enter button. This is the time the test starts. It doesn't matter whether it arrives in at the server in time or not. There it starts. And the second thread takes the prepared request and tries to send it as fast as it can, and takes the end time. And the difference between those 2 times is latency, because it includes the wait time, this first component here. This will get a little bit clearer in the next slides also. But now we have to take a little side topic first, which is throughput. What throughput is, think of your system as some kind of pipeline, which is pulling work and turning pink thingies into blue ones. And you have 3 processing stages, so it's keeping pushing, right? And if you look at your system, take a snapshot at some point in time, let's call it n, it looks like this. Now you wait for a second, and it looks like this. So when we are contrasting those 2 points in time and looking at how many operations it could process within the second, we obviously arrive at 5 operations per second, right? Because at second n we have the request number 1 retired, or we're finished processing, and 1 second later we got request number 6 processed. So there are 5 in between. This means in 1 second we get 5 operations per second. So back to latency. Imagine you're driving to work, and let's pretend you're an extreme early riser. You're driving across Mitterdorfer Ring at 4 a.m. And let's say this will take you from your home to your work 20 minutes. Now what happens if you do the same thing at 8? You probably won't arrive within 20 minutes, right? And let's call this time, your driving time, the latency. And what happens on the street is the throughput, or if you can also call it utilization. Utilization goes from 0 to 1, and throughput is an absolute number with a dimension. How's the street utilized at 4 a.m.? It's around 0, right? It's maybe there is some other crazy guy which is also driving to work at 4 a.m. besides you. But at 8 a.m. There are probably a lot of people driving to work. So the street is completely utilized, but nobody is making progress. And we call this a traffic jam. And now imagine if you do the same to a server or to an application. The same thing happens with your latency. So this means if the utilization is very low, requests get through, there are no queuing effects, no queues building up, right? The requests get processed as soon as it comes in. But as more and more requests pile up, as the system reaches its maximum utilization, all kinds of queues will come in. For example, even before they enter your application, the operating system has a network stack which queues things. Your application probably also has queues, so a lot of queues involved. And there you will drive up latency. So it doesn't make really sense to say my latency is this and that. You have to say my latency is this and that at this throughput. And this is the last thing we need to add. We need to wait a little bit, because we need to, in our generator thread, we can't just hit the system as hard as we can, because then latency will go up the roof. So we want to define some kind of sane target throughput. Say your maximum throughput is 1000 operations per second, then you may want to benchmark at, say, 700, because this is where you would operate your system in production also. You wouldn't drive it at 100%. It wouldn't make sense. Is this clear so far? I think this was the hardest part of this talk. Okay, seventh and last sin. You also can't treat performance as one-dimensional, especially not in our case. We can't just say, yeah, we reach throughput of 2000 documents per second. Under which circumstances? With which data? With which bulk size? Which query parameters did we use? We need to vary this, because otherwise this is useless to say. Also, maybe we want to vary execution order. This is where your question comes in. We want to interfere. We want to run queries in different orders. We want to interfere operations. We want to know when we index how the search behaves then. And to be honest, currently Rally can't do this, but it's on the roadmap. It will be able to do this soon. And the last thing is, you also maybe want to run on different hardware, different operating systems, different JDK versions. And finally, I will relieve you with the summary, with a very short one. I hope you've seen that you should approach this topic scientifically. You need to have a reproducible environment. You have to have reproducible procedures, how you run your experiments, what you expect from them. You need to be able to explain the results why is the performance so low or high or whatever, and you need to introspect and critically look at the results. I like this quote from a JVM performance engineer. He says, performance is easy, all you need to know is everything. I can just agree to that. It's a vast field and there's a lot of topics you can address. Yes?
Since the systems are also I/O heavy, have you also gone through and looked at actually the general I/O performance of the machine itself? Because in a production environment you have multiple things going on which actually interfere with the sort of I/O of the machine itself, which then really changes things, which is why, for example, like the number of threads, if you don't have this thing going on, you're going to get a very different kind of thread response than when you have other things going on because of data bottlenecks within your cores.
Do you refer to I/O performance as peak performance that the hardware can achieve? So we ensure that we don't saturate, that we don't bottleneck on this, or I don't know what you're referring to.
Your machine has bottlenecks.
Yeah, right.
And the way you're doing it now, and it's not in a production environment, you're not actually picking up some of those effects as when there are other things going on which are actually sort of taking up other resources.
I don't want to do this actually, because we don't have production. That's the thing. We're a product company. I want to have a lab environment. I need reproducible numbers. I need to tell, because if I run some kind of random parallel
parameters without, it's not under production, not under strain, some of the parameters look nicer, and in fact the number of threads and the numbers of things you want deployed may be different depending upon the other sort of environments, the other sort of things going on with your server itself. At least when I did these numbers some time ago, that's what happened.
We may need to talk after that. I don't follow it at the moment. Maybe it's just because I was talking. I don't know. Let's talk afterwards. Anybody else? Yeah?
Yeah, now since that you open sourced Rally, is it also intended to be used by customers to benchmark their own system once they know they have their own data and they probably know about their own queries, and essentially building their own tracks? Is this?
Yeah, customers already do this.
Okay.
Yeah, we have one limitation at the moment. You cannot. The benchmark driver is at the moment limited to one machine. I restructured the application currently that it's possible to distribute this. And if you want to have distributed benchmarks, you also need to provision the cluster by yourself. That's also on the roadmap for the version after the scalable benchmark driver. But customers already use this with their own tracks, yes. That's starting to be picked up externally. Okay, done. On to the beer, and oh, I forgot the most important slide probably. The meta slide. I'll also post it as a comment then on the meetup page. Thanks.
You promised links, further links on this somewhere? Awesome.
Yeah, there. Also the image references. But you probably don't want to see them yet. No. Okay. Thanks a lot.